Hello everyone, I am Quentin Félix Adam, PhD student at the Technical University of Denmark, and I would like to present a research topic I am currently writing a paper about, utilizing an electric snow melting system to protect asphalt pavements against low temperature cracking. This work has been prepared with my supervisors, Associate Professor Eyal Levenberg and Associate Professor Thomas Ingemann. Pavement surfaces in cold regions are exposed to weather events such as snow accumulation or ice formation. These hinder user safety because of the drastic decrease in skid resistance and also because of the masking of road markings. For the specific case of asphalt pavements, the most common pavement type worldwide, an emerging solution for tackling snow and ice at the right surface is electric heating in the form of embedded ribbon elements, as demonstrated here on the campus of the Technical University of Denmark with the infrared picture. One advantage of the electric heating technology is its agility. In other words, its ability to provide on-demand heat energy. Last week, a snowfall event occurred in the region of Copenhagen, and the heating system embedded within the road presented on the previous slide switched on. Here shown is the capability of such an embedded system to melt snow. On the right picture, stripes can be observed on the asphalt, indicating clearly the position of the heating ribbons. Furthermore, asphalt pavements in cold regions are prone to low temperature cracking, starting from the surface of the pavement. This stress is typically manifested by transverse cracks that appear after an isolated event of fast cooling in combination with low temperature levels, or due to several cooling cycles that ultimately produce a microcrack. Due to their large lateral extent, asphalt layers are restrained from horizontally deforming. Therefore, fluctuating temperature conditions cause a buildup of thermal stresses. Specifically, low temperature cracking is induced by tensile thermal stress exceeding the layer tensile strength. This work addresses the case of an electrically heated asphalt pavement with ribbon elements. It explores an unconventional application of such a system, not for combating snow and ice, but for mitigating low temperature cracking due to a fast cooling event. The objectives of this paper are to demonstrate that the overall idea of utilizing such embedded heating systems to protect asphalt pavements from low temperature cracking is sustainable. To this end, computer-based calculations were carried out, in which real weather data was utilized. The thermal and mechanical fields were decoupled. The thermal formulation considered the heat equation applied to a three-layered half space to acquire the surface temperature, while the mechanical formulation considered a three-dimensional thermoviscoelastic equation to acquire thermal stresses at the surface. A right-handed Cartesian coordinate system is introduced at the surface of the half space, with the z-axis pointing down into the medium. Assuming identical thermal properties and boundary conditions within any plane perpendicular to the z-axis, the one-dimensional heat equation is utilized. The formulation includes an internal heat source Q to represent the operation of an array of electric ribbons. Additionally, effects of moisture freezing and thawing within a layer are considered as well. Here represented is the model three-layered half space. The top layer, layer 1, represents an asphalt concrete layer. The middle layer, layer 2, represents an unbound granular base, and the bottom layer, layer 3, represents the subgrade and deeper soil mass. The upper boundary consists of an energy balance at the surface, controlled by weather effects. In this work, the shower radiation, convection effects originating from the airspeed and the air temperature, as well as the long radiation are considered. A zero heat flux serves as a lower boundary at a depth of 20 meters. The heat source is placed at the depth ZR. The thermomechanical model represents a layered half space which extends to infinity in the x and y directions. With the change in temperature level, this representation does not allow any deformation within any plane perpendicular to the z-axis. Under a change of temperature delta T, this means that the half space does not experience any stress in the z direction and stresses of equal magnitude along any direction within planes perpendicular to the z-axis. The mechanical formulation aims at quantifying the thermal stress history specifically in the xy plane, where the low temperature cracking typically occurs. For this, a linear viscoelastic solid constitutive relation is selected, governed by one-dimensional relaxation modulus and a Poisson's ratio. This linear viscoelastic formulation utilizes the temperature superposition principle, assuming that the asphalt material in layer 1 is thermorelogically simple. The weather effects introduced in the thermal formulation are quantified by utilizing real weather data measured by a weather station in Nuuk, Greenland. Here presented are four charts, with the x-axis representing the time on all of them, with the American date notation format, months and then day. The y-axis on each of the charts represents one of the measured entity, namely the air temperature, the shower radiation, the airspeed, and the relative humidity. The shown data represents a typical year in Nuke. For example, the summer and winter periods are clearly identified on the air temperature chart and can be correlated to the shower radiation chart, where most of the radiation occurs in the summer. This data was utilized to calculate the temperature at the surface of the model domain. I would like to focus on the period within the red square, during which an event of cold temperatures occurred. Based on the presented mechanical model, the thermostress were calculated for the period identified on the previous slide. Here represented is the chart with the time on the x-axis, specifically between the 13th February 4 am and the 14th February 9 am. The thermally induced stress are placed on the y-axis, with tensile stresses taken as negative. It is considered that the asphalt material has a tensile strength of 2.5 MPa. Here is the evolution of the thermostresses for the calculated surface temperature. As can be seen, a crack would have occurred at approximately 8 am on February 14th. Then, thermomechanical calculations were repeated, this time with the heating being activated 30 minutes prior to the identified cracking event. It is considered that each ribbon carries 40 watts per linear meter, and that ribbons are spaced 20 centimeters from each other, center to center. Now represented is the thermostress evolution with the heating activated, and as can be seen, the stresses do not reach the defined tensile strength. With this simulation, it is demonstrated that utilizing an electric snow melting system to protect asphalt pavements against low temperature cracking is deemed possible. Thank you for your attention. Should you have any question, I will be glad to answer them.